Hello everyone. First of all, thank you all for coming. I wasn't expecting so many people here because usually genetic algorithms is not something people show up to. So my name is Raman. And I will be talking about genetic algorithms today. And I initially planned to divide my session in first 15 minutes explaining what genetic algorithms are. I thought of dividing my session in first 15 minutes to talk about what they are, and then next 15 minutes how to implement them. But then I recently attended David Weasley's talk, and he did his complete talk on hands-on, and I get over inspired by that. So my talk is going to be complete hands-on. So a little bit about me. I'm a CS undergrad, and I'm also a co-organizer of PyData Delhi with Sanket and Arsh. I've interned at Timeless, Audacity, and Polarity. And if you like the talk, you can maybe follow me on Twitter or get in touch with me. And I will just directly start, okay? So when I was a kid, I always wanted to create my own world because I thought that the world is maybe just an algorithm, and that algorithm is running, and that's how the world is working. I couldn't do that back then, but now I'm going to try creating that. So what exactly I'm going to do is I'm going to create a world where there's this area which is 1,000 in length and 10 in height, and there's this car in the center. There are going to be many cars in the center, and I'm going to teach them how to cross this road, or maybe how to remain in this area, and I'm going to use genetic algorithms for that. So you should visualize this right now, because I'm not sure how much visualization I have. To do that, first thing we're going to do is we're going to create our car and define the properties for it. Okay, I literally had nightmares when I was thinking about presenting it, because I can there are so many things that can go wrong. And maybe I want you to help me out here, okay, if I do something wrong. So when I'm creating this car, I'm giving it an ID, and it can be I'm gonna import from random. I'm gonna import choice, right? Choice range. And then I'm going to decide a step size. So what step size is, let's say if car starts, what's the maximum size a car the car can take, the maximum distance that car can travel. So it's going to be step size that I think I will go for 5. So as I showed you earlier, the road is 1,000 meters or whatever unit is that long. So one step that the car can take, it's going to be 5 meters. That's what it means. Then I'm going to just keep a track of steps taken, and for now it's going to be 0. And then I'm going to decide. So right now the car is at 0, 0, so it can go from 0 till 180 to go straight forward. But so 0 here is the minimum angle, and 180 is the maximum angle, and that's and between that we can pick any angle, okay. So I think that's all right. Yeah. And then I'm going to teach it, like I'm going to create a function where I'm going to define that how the car should move, where I will just say that while true, just okay, first I'm going to create the current x, current angle, it's going to be, I can't remember, what is it? So what I'm trying to do here is I'm going to pick an angle. Okay, yeah, I remember. So I'm going to pick an angle between the minimum angle and the maximum angle. So that is like, okay guys, is it okay if I go to my backup plan? Like, I'm really sorry, I literally created this talk like last night. Okay, so I'll have to go to my backup plan. I knew this might happen, so now I can explain you little faster and little better. So step size, as you know, the step it can take. Steps taken is like how just to keep the track of steps taken, the minimum angle and maximum angle. So in general algorithm, there is this one important thing called fitness, which is exactly which we have in natural world, that when we have different species, they have different chromosomes, and each chromosome is like different in fitness. Some chromosomes are like more fit, some are not, and that's what it is. The X list is where I'm going to keep the track of all the x-axis that particular chromosome is going to go to, and the same for the Y. Mutation rate is like how many the mutation is not something which happens all the time. It's something which happens like only few times, so that's what it is. And mutation step is how much do you want, like how much it should mutate. In run, I'm telling that right now the car is the current x is 0, the current y is also 0, and that's what I'm storing here. And I say that while true, the car can move, but car cannot go beyond this y-axis and this y-axis and the x-axis. So that's what I'm defining here. I'm telling it that you cannot go, you cannot be more than the height, like the half of the height, and cannot be less than the half of the height. You cannot go beyond the length of the road, and if you do that, it's gonna break, and then it's gonna calculate the fitness. And then I'm choosing like a random angle, and I'm converting into radians because that's what is used in like to get next x and y axis. And then I'm just appending it like in my x list and y list. Then I'm just increasing the steps taken. Okay. So till so far we have just defined that how the car can move, and now there's this other class which is called world, where we are going to define the population size, that how many cars we want in one generation, and then we're going to define current generation we are like right now at, and then this is the maximum generation. So when we're going to start this program, it can run till a particular point. So that's what max generation tells us, that once you have reached 100 generation, you can stop now. This is just the width and like the length of the road. This is storing the cars, like the like 100 cars according to the population, how many population is there. This is for the history, like to store each and every generation and how many chromosomes it had, how many cars it had, and then that's all. This is to start the function. where again I tell that till the time it's true you can okay, I'm gonna do one thing. Okay, I'm gonna go to an old slide where I'm gonna define the concepts. Okay, I think because I initially planned that I'm gonna do a hands-on, but I think I'm not prepared that well. So I'm just going to go to an old talk which I gave when I was like starting to learn genetic algorithms, and I'm going to start again, and I hope you have a good experience after this. So first I'm going to talk about the origin of genetic algorithms or genetics in general. They come from, so each one of us have heard of Charles Darwin theory, like survival of the fittest and the mutation. That's we take that theory and we apply it in computer science, and that's how we come up with genetic algorithms. So initially life started with single cell, and they used to divide themselves into two different cells. When they used to divide themselves, some error happened, and because of that, like errors are actually mutation only. So mutation happened, and they started doing photosynthesis. Then after photosynthesis, some more errors or some more mutation happened, and then eukaryotes came in life. And after that, they started eating each other, and that's how multicellular organisms came in life, and that's how complex life started. It was like discovered by Alfred Russel Wallace and Charles Darwin, and they together created this paper on the origin of species, theory of evolution, in which they again told, like they pointed out two things. In computer science, it was applied by John Henry Holland, and he wrote, like in 1950, he wrote this paper called Adaptation in Natural and Artificial Systems. So genetic algorithms are basically search-based algorithms. So what they do is they search for the optimized solution in a given solution space, and they try to find the best solution in that. And they are not exactly something you would want to use for some, like to train something. They are usually used when you're trying to solve a NP problem and something that for that solution exists. And this is basic structure of a genetic algorithm. You first start with initial population, where you define some properties, which I was trying to do. Which I was trying to do here, like I was trying to define the properties here, and then you try to solve the problems. Once you solve all the problems, you pick the fittest population out of them, fittest solutions out of them, and then you cross them over, and then you mutate them. And after mutation, you keep repeating this step till the time a termination condition is reached. And usually that termination condition is either that the problem you were trying to solve is solved, or there is a particular generation you wanted to reach that you have reached. This is like the pseudocode for the genetic algorithms. Again, that's the same thing. So okay, I can maybe show you an example. So this is something I was trying to create a while back. I'm not that good at presentation stuff, but I like to create that. So what I was trying to do here is I was trying to teach that mouse to reach the cheese, otherwise that mouse will die. And in that I purely used genetic algorithms. But you can definitely find multiple examples of genetic algorithms where people have trained cars or a GA to play even the arcade games like Mario and other games. Going back to it. Okay, I just finished it really early. No, okay, so the point was that genetic algorithms are just tool. You can like it's on you how you use them. It's like it's hard to write them, but if you know how to write them, it's like very easy. I think I'm really sorry, guys. Like, I know you came here with huge expectations and all. I was prepared as well, but I mean, I saw Peter Wang in the audience and I was like, okay. And then I saw James Powell there and David here. It got really overwhelming for me. But if you have any question, or if you want to like discuss something, please be easy on me, please. I'm dying inside. Huh?
Oh, so the car demo, it won't work if you show it?
It will actually. It will. That's it will. That was. Okay, I might have to change something. Mm-hmm. Nope. Let's see if it works now. It does, but it will keep on going like that, so I will have to decrease the generation number. So what I did here was earlier I was trying to train it till 100 generations, but now I decrease it so it will complete really fast, though not sure if the results will be that good. Okay, I'm doing something wrong here. It worked, like when I earlier tried it, it worked. It's not working right now.
So while Raman tries to sort out the demo, just to give you a nice demonstration, why don't we give him a round of applause? I think he's For those of you in the back, I don't know if you can see the beads of sweat rolling down his head. Everybody has difficulty with live demos, and so I really think that we should really appreciate Raman coming here all the way from Delhi to give this presentation. I know it's very stressful doing live coding. I think we have a little bit of time left in the session, and there may be an opportunity for everybody to have an open conversation about this topic. It seems to be a lot of interest. We have some people who are experts. Even Steve here, who's one of our presenters, has a PhD in genetic algorithms, even though he won't admit it. Anybody? And so, Raman, if you'd like to kind of open it up and see if there's any questions from the audience.
Yeah, if there are any questions, please.
I'm using genetic algorithms.
Uh-huh.
It takes a very long time to get those signals, wide signals. Is there any experience of yours how to go about finding this?
So before we get exactly to that question, you're using this at your work. Is anybody else here using genetic algorithms in their actual work and just saying deep learning, no thank you? How many people? And so any experience, Raman, or from anybody in the audience about finding the right parameters for a genetic algorithm?
So when you say trading, you mean stock trading, right?
Yeah.
So you
It takes a very long time.
Yeah. I think, and it's been a long time since I've touched any actual trading algorithms with these things, but for the most part they train on history. And so you use historic data to predict more recent historic data.
Yeah, that's what I do.
And then, but the idea is that you find the parameters that way through simulation, which you can do as quickly as we're seeing.
The thing is, I have to do it for all.
Yeah.
If you increase the population of the generation, it gives you better signals.
And it
but
takes a
takes
lot. Yeah, it
a long
does.
time.
This is one of the biggest embarrassingly parallel problems that exists. The fitness evaluation, which is the score for how good a set of parameters performs, is it's terribly slow, but it's completely independent from another set of parameters. So some of the experimentation that has gone on over, I'm going to say -5 years, because I haven't touched this field in quite a while, but prior to that, the 10, 15 years before that, has been MPI distributing the process, some GPU work, but that was very early on in GPUs being a big thing, so there's probably been more since then that I'm not familiar with, but it is, it's tuning those parameters. The whole thing is a parameter tuning process, right? So it's like, you can't apply a parameter tuning process to the parameter tuning process, or you can call it hyperparameters and get more funding, but that's, I mean, it is a parameter tuning process, so scaling up. The two most interesting things I would say about that are, so certainly genetic algorithms is not the only algorithm in this class, and there are other similar algorithms that have higher rates of convergence, or they're more greedy, so they're going to get to a good solution faster. And so those are always worth investigating. But there's also, and I think my advisor was playing with this at one point, caching results, or adding a prediction algorithm that, based on the change we made to the parameters, so the amount of mutation or what actually changed as part of that mutation, we can predict what the quality will be without actually calculating it. And that was an active field of research nearly a decade ago now, so I don't know exactly where that's landed. But I think the target was actually for investing and those kinds of decisions. So, now the questions come.
Now the questions come. How about in the blue?
So kind of what I see right now is that the enthusiasm is behind reinforcement learning instead of this, but I don't really know why. Is that just intractable? Is it?
And if I may add on to that, Raman, why choose this topic rather than one of the very popular topics about deep learning, reinforcement learning?
Well, because I've been playing with genetic algorithms for a while now. I might not be a good presenter, but I like to I really like genetic algorithms, and as far as I think, they are used as a supplement with other things. If you use them individually, they are powerful, but they're not as powerful as other algorithms are. But I still like to play with them and create things just using them. So I created the rat AI. I created a Tetris AI, which plays the Tetris game, and I thought to choose a very simple example of teaching a car to cross a road using genetic algorithms. I was able to do it even last night, and I don't know why I wasn't able to do it now. But
live coding is tough. It's if you can code it on your own in 5 minutes, you might be able to live code it in an hour. It's that time.
I'm gonna. I guess David Weasley don't know it, but I'm gonna blame him for this. I was in PyCon Chennai recently, and there he gave a keynote, and at that time I was submitting my proposal for here, and I attended it, and he was brilliant in it, and I thought I got a little over ambitious, and I was like, maybe I can try that.
Was there another question in the second round?
Or if I can just add on to that question, the reason you wouldn't do it is it's solving a different problem. So I describe genetic algorithms or evolutionary algorithms generally as parameter tuning. And so those of us kind of who have that background look at the parameter tuning people do with reinforcement learning, and they're like, yeah, we do gradient descent. And we're like, oh, that's our baseline for all of our algorithms are better than that. And if they're not better than that, they're a waste of time. They don't even publish. So it's solving that. So you could use these as a replacement for the gradient descent parameter tuning that all of those algorithms use, because that's the problem it's solving. These don't actually get you a reproducible algorithm for converting text into speech. They get you a set of parameters that are really efficient for some process that you already know how to do. Sorry, what was it? Thanks for the next one.
So, two-part question. One is, it seems that the genetic algorithm could get stuck in local optima. So do you have any advice on tuning the learning rate with respect to the number of generations that might help avoid that? And then kind of in a similar vein, do you have any advice in terms of setting up the initial population size with respect to the number, like the size of your chromosome to achieve a fast result?
So personally, I set my initial population very less, and the reason is because the power of genetic algorithms are in mutation. So if you set the population very less, the mutation will automatically happen more faster. So I generally advise to set it on like this. If you're asking about like what's the general advice on setting a population size, I will say try to set it like 100, 200 or very less comparatively. And what was your first question again?
On whether there's a trick with respect to setting the mutation rate relative to the number of generations existed?
Right. So it's like personally what I do is I set it around 10 to 20%. Like it only happens 10 to 20% of the time. That's all. Like it's a personal choice though.
And when you start digging into the other algorithms, these are where they differ. So honestly, and I hope this is. Are we still recording this? Is this going to go online? Okay. Various algorithms kind of come with a preset mutation rate, which they'll call different things, but that's why they perform differently on different things. But fundamentally, it's a single parameter, which is the mutation rate. It's the rate at which things change randomly from iteration to iteration, and that's wildly adjustable. And that's just something that you have to adjust. And you end up having to design these things, and you'll run it for a while, and you'll watch the rate of convergence, and go, oh, that's too quick. That's not going to end up there. It's not quick enough. When you start looking at the papers in this field, it's a lot of run the experiments over and over again and get a general sense of if we tweak this number, where does it end up? But it's always application specific, it's always task specific, it's algorithm specific, it's representation specific. It is something where you have to design the whole thing holistically, and it's really difficult to pick up, just pick up genetic algorithms and apply it, because that's not taking at all into account the thing you're actually trying to do with it. And I think the one other thing I'll say is in terms of the number of generations is a stopping condition. You don't have to specify a number of generations. That's just eventually you get bored of waiting for it, and so you tell it to stop. And ideally, you have a quality of solution stopping condition, and so you stop when it gets a really good answer, and if that takes 10 generations, great. If it takes 10,000, also great, because you've got the quality of answer. But it's very, very rare that you would say, we're going to go with the best we have in 100 generations. And I think the exception to that is probably the traveling salesman problem, which is what FedEx and UPS and everything use, because they need an actual map to go deliver these packages today. You can't let that run indefinitely. At some point, you have to say, oh, this is the best route to visit all of these places. We'll go with that.
I've used simulated annealing to set parameters for models.
Yep.
How does it compare to genetic algorithms?
Like I said, do you have
What was the question again?
simulated annealing?
No.
Nothing at all. So again, the inspiration is a prominent difference. I actually had at one conference many years ago the creator of one of these algorithms shout at me for suggesting that they're all very similar algorithms. And he said, no, but my one uses bees and their one uses birds, or something like that. But fundamentally, it's the inspiration. that kind of determines how. So simulated annealing is, the idea is when you heat up metal, then it causes more motion of the particles within the metal. And as it cools down, they settle into a different arrangement, a more stable arrangement, and that's called annealing, and you end up with stronger metal as a result. So it's a simulation of that, where you add more entropy into the data and have an algorithm whereby things settle over time, the hope being that they settle in a better configuration or better values. And so, in a sense, it's kind of like you have mutation going on, and it's iteration to iteration, you've mutated it in some way, but it's not random so much. It's like you've started from randomness, and you're trying to reduce the mutation over time, which genetic algorithms does that with crossover, to try and reduce the variation over time. And this is more like evolution strategies, which doesn't use crossover. It's just like a straight, let's adjust the values to try and reach convergence. So it's similar in that you start with randomness, and you're trying to reduce that while improving quality over time, which is a very, very broad statement, I understand. But yeah, it's certainly on that spectrum of gradient descent through to these algorithms is somewhere in between those two. Most people would not consider it an evolutionary algorithm, so yeah, but it is similar.
Do either of you have recommendations for resources in getting started with genetic algorithms, or even say like domain-specific applications of genetic algorithms?
To get started in it?
Yeah, like any, say, like really useful texts you found that were.
What I usually do is I go on GitHub and look for the examples, and I try to understand them from that, how they're doing. And if I get stuck somewhere, I then go to the actual the Wikipedia and stuff to read about it. So that's what I would recommend.
I have an entire PhD if you want. No one else has, so I mean. No, it's been a very long time since I learned all of this stuff, and I got started in the context of original papers and all of that. I can hardly recommend that. That's not a great place to start. But everything that I did read on getting started does tend to treat these as independent algorithms, and very few will satisfy the engineer who's looking for the genericness of it all.
Gotcha.
So if you are going to get started, I would look up Introduction to Genetic Algorithms, one for evolutionary programming, one for evolution strategies. And by seeing three things that are fundamentally the same, where the authors claim that they're entirely different, then you'll get a much clearer idea of what's actually going on here. So I would recommend that. And a lot of the code on GitHub, I would not recommend. I would go for books on this one. This is very much an academic field, not a practitioner's field. So there's not a lot of production quality code in this area. And where it is, it's highly proprietary, and the companies that have it mostly won't even admit that they have it. So yeah, books written by professors are probably the starting point for this. One or two more questions, Kenny?
Yeah, so question kind of about determining the fitness function with your kind of rat example, where it was just kind of going through past two walls. How would you kind of define that? Where would you change the fitness function, kind of assuming it's, closest to the cheese is the fittest rat? What happens in a maze where you can get to the closest point, but then there's a wall in your way and you'll never actually reach it if you traverse that way? So now your algorithm spends all that time looping to get as close to the cheese as they can, but now it's kind of stuck in, I guess, a local optimum, right, where it'll never actually get to the right answer.
So fitness function does not have to be just one parameter. So it is not really necessary to just count the distance between the cheese and the mouse. You can also count the steps taken, how many steps the mouse was able to take. So the more steps it was able to take, this is just an example. So one thing can be the distance from the cheese, and the other thing can be the steps taken. And it's actually very subjective, so it depends on the problem. And I haven't really thought of how will I calculate the fitness in case of a maze, but I would definitely consider these two things.
It's a great example of local maximum, just in general.
Yeah,
You can see that, right? It's you get to the end of the maze and you know it's right there, and every single algorithm that takes the distance, like the proximity to the goal into account is going to hit a local optima there and never get out of it. And yeah, I don't know how I designed fitness function for that either.
Yeah.
But the amount of steps it takes, I mean, make the rat starve. And it's like if it doesn't get there within 50 steps, then it gets 0 points. And everything about its path is then going to be ignored for the next generation because it's the lowest fitness rat.
But you know the correct path, so you could.
If you know the correct, yes, but then why are you applying an algorithm to find something you already know?
Well, for trading, it's the total gains.
Yeah.
Gain.
Okay, one more? Or if there's no more, then we can get to the coffee before everyone from the other talks.
And let's give Raman one more round of applause.